All right, this is the lecture video for day 23. We're talking about confidence intervals today. So last class I spent a while talking about this idea of statistical inference, how if we have information about a sample, as in if we've tested something on a small scale, how can we apply that to the population? How can we say something bigger about, let's say, the real world? I talked about that for a while, but all we actually got to were probability distributions, which were hypothetical, but still probability questions of if we understand the rules of the game, what types of samples do we expect? All right, today we're actually going to be doing some inference. All right, so the question that we have for today and moving forward is if we know something about the sample, if we have a sample statistic, as in some summary of what the sample is doing, what can we say about the population as a whole? Today we're again going to be focusing on this categorical case. We're talking about percentages of a population or percentages of a sample that fall into one category or the other. Next time we will work with the quantitative case, where we are talking about both the mean and standard deviation of some quantitative variable. Looking on down the line for the rest of the semester, we're going to be doing a lot of things twice. We're going to be talking about how we would do them for categorical variables, and then how we also would do them for quantitative variables. For each of the statistical inference tasks that we plan on doing, there's a lot in common between the quantitative or categorical approaches, but there are still some fundamental differences. Okay, so let's jump into this idea of confidence intervals with an example. All right, so if I flip a coin, assuming it's a fair coin, then there's a 50% chance that it comes up heads and a 50% chance that it comes up tails. So with that, I would say P equals 0.5, where the event that we're paying attention to is the coin comes up heads. If I were to instead flip something different, so here I have a bracket that's used to hang things like paintings on a wall. And if I drop it, then it typically either lands on its side like this, or it lands flat on its back like that. So one question I might have is, what's the probability that if I drop this, it lands flat? One way to figure this out would be to test it, to randomly roll this or flip it some number of times and record how often it is that it lands flat versus how often it lands on its side. So given the way the bracket is shaped, given what it's made of, given all these criteria, there is some inherent probability that it lands flat. That's just a property of this bracket. The question is, how can we figure out what that is? How can we determine, or what can we say about P, where P is that probability, the probability that it lands flat? All right, so I tested this. I flipped it 10 times, and out of those 10 attempts, it landed flat 6 times. So does that mean that our proportion, our P equals 0.6? Does that mean that this bracket's fundamental probability of landing flat is 60%? Not exactly. Just because these 10 trials had a rate of 6 out of 10 doesn't mean that that's necessarily what's going on. So the information that we do have is that this particular sample had a rate of 0.6. So we're denoting that difference with P hat as opposed to P. What we want is P. We would love to know what this proportion is. Instead, all we have is what happened for this particular sample. We want to ask ourselves, if hypothetically the actual proportion, if hypothetically P did equal 0.6, how likely was it that our sample ends up with 0.6? So this is a question that we could have asked last time. The answer ends up being about 25% chance that 6 out of 10 times it lands flat. But if the probability instead was something like 0.5, there's still a 0.2 chance. If the probability was 0.4, there's still a 0.11 chance that this 6 out of 10 just happens to happen. So this 0.6 is certainly our best guess for what the population proportion actually is, what the real value actually is, but it's still just an estimate. And so 0.6 is a good guess, but we want to be able to talk about what a realistic range of values would be. If I tested this and it came up 6 out of 10 times, and we later found out that the actual value was 61%, well, that shouldn't sound surprising. Even 50% shouldn't sound terribly surprising. If, however, someone said that the actual value was like 10 or 1%, that should be surprising. So the question that we want to answer is, where do we draw the line? What are the range of values that we think are reasonable for this p-value to take? So our best guess as to what p is whatever our sample was. So our best guess is that it's 0.6, but in order to get a sense of what the error bars should be, we're going to use this thing called the standard error. So recall the standard deviation for p hat. So if we happen to know what the population's proportion is, if it happened to be the case that this bracket lands flat 70% of the time, if we know that that p is 70, then we can calculate the distribution for what a sample of size 10 would look like. So that's going to be the square root of p times q over n. Right. The problem is that we don't know what p and q are. We know what p hat is. We don't know what the actual value is. So what we're going to do is we're going to estimate it. We think that the value of p is about p hat, so we're going to estimate this equation with a very similar looking one, p hat q hat over n. And this is a very similar idea. Obviously these equations look very similar, but rather than calling this the standard deviation, we're now calling it the standard error. Just to point out that, hey, this is an estimation of what the actual sampling distribution should look like. If we happen to know what p was, then we could find the exact sampling distribution. Since we don't know that actual value, we have to settle for the standard error, which is an approximation of this distribution. All right, one quick aside for these things called critical values. We're going to need these in a moment. A critical value is really the z-score for which a certain percentage of the normal distribution lies within that many standard deviations of the mean. So the critical value, put another way, for a given confidence level, for a given percentage of the distribution, for example, 95%, the critical value, this z-star number, is going to be the number of standard deviations away from the mean we have to look to find that much. So what I'm asking here is, how many standard deviations away from the mean do we have to look such that 95% of the distribution is in that range? And this is something we've talked about before, right? We have the 68, 95, 99.7 rule. That's saying that we have to look 2 standard deviations away from the mean to encompass this much. So the z-star here would be 2. Actually, we're going to be a little bit more exact and say that it's 1.96, just to be a little bit more technical. The critical values for these other confidence levels, common ones are things like 90% or 99%, and these other values are 1.64 and 2.58. Put another way, if we go 2.58 standard deviations away from the mean, and we talk about all of this portion, well, this is going to be 99%. Probably the most commonly used confidence level is going to be this 95%. We're going to see 1.96 crop up a lot in a lot of things we work with, but these other values, these other levels certainly have their place. So back to the question about the bracket. our best guess for what P, the actual probability that this bracket lands flat, our best guess for that is P hat, or the sample proportion that we found, aka 60%. Still, our best guess for what this probability is the probability that we saw when we tested it. That said, the quote-unquote error bars, the range of values that we think are still reasonable, are determined by a few things. They're determined by how much information we have, which comes from things like how big our sample size was, as well as how specific, how certain do we actually want to be. Let's stick with the middle ground. Let's go with the 95% confidence level. So we're going to construct this thing called a confidence interval, which we do by taking our best guess and saying that we think the actual value is 0.6, give or take a certain number of standard errors. By the way, if we ran the numbers on this, we should see that our standard error in our 6 out of 10 example should be about 15.5%. So if we want to know the confidence interval, then that's going to be our P hat, our best guess, plus or minus a certain number of standard deviations, a Z star of 1.96 times the standard error 0.155, which gives us a range of values ranging from 0.3 to 0.9. So our 95% confidence interval says that we are 95% confident that the actual probability for that bracket is somewhere in this range, which is a pretty big range. And it's that big because our sample size was so small. Our standard error is very large. 15% is a pretty large standard error because we're only dividing by this small n. So I want to also draw this on our number line here. Our interval is going to be centered at this 0.6, at this P hat number, but we are going to look a total of 1.96 standard errors above and below. So our lower range is going to be 0.6 minus 1.96 times 1.55, which is very close to 0.3, or 0.6 plus 0.3. So our range is going to be from 0.3 to 0.9. Anything in this interval is a reasonable guess for the probability that the bracket lands flat. All right, so we know how to find a confidence interval. We can go through this process. We can calculate a range of values that form this interval, but what exactly do we mean by it? There's a little bit of subtlety as to what exactly this number means, and it certainly is related to probability, but we just have to be a little bit careful with what exactly we say. So I've said before, a lot of this logic hinges on hypotheticals. So if I were to do this entire process over and over again, I'm talking flipping it 10 times, recording it, calculating all of these things, calculating the standard error, and then calculating the interval. If I were to go through that entire process a whole bunch of times, I would construct a whole bunch of intervals. The 95% confidence is saying that 95% of those instances, that 95% of those intervals are going to happen to hit the actual p-value. All right, so here it is very tempting to say that there is a 95% probability that the interval includes p. And the reason that we can't quite say that is that that implies that this p-value is what's moving. Instead, the random component happened when we chose our sample, happened when we actually flipped the bracket a certain number of times. The population parameter p has been fixed the whole time. That's not moving. It's the interval that happens to be doing the moving. So a common phrase will be that we are 95% confident that our interval includes the actual value, includes the real, quote unquote, value of p. All right, so when choosing our confidence level, there's this inherent trade-off between certainty and precision. If we choose a higher confidence level, we'll be more certain about where the actual population parameter is. However, we'll be a lot less precise. We'll have a much bigger window to deal with. So let me draw a couple of these using our example that we've been using. If our sample proportion was 0.6, it came from a 6 out of 10 sample, then the 90% confidence interval is going to be 0.6 plus or minus 0.15, whereas the 95% interval is going to be 1.96 of these, and the 99% confidence interval is going to be even bigger. So if we are more confident, as in if we have higher certainty, that goes hand in hand with having a larger window, which means that we're being a lot less precise. At the 90% level, we actually have a relatively narrow range as to where we think the population parameter is. However, we're not terribly sure about it. And we don't even have to use these confidence levels. These three are certainly the most common, but we could use any particular level. Let's say the 50% confidence level requires a z-score of only 0.67, I think. So in this case, our confidence interval would actually be a very small interval. So, we're being very precise. However, we are not all that certain. So it's a trade-off going one way or the other. All right, so what if I want both? What if I want a very precise estimate that I'm pretty certain about? Well, we can get both. The way to do that is to have a larger sample size. So our standard error equation that we were using earlier has n in the denominator. So as n gets bigger, as our sample size gets bigger, the standard error, or aka the width of these intervals, is going to decrease. So let's say that I wanted a margin of error, aka the plus or minus part of the confidence interval. So let's say I wanted a margin of error of only 5%. So if I want a margin of error of only 5%, at a particular confidence level, let's say I want to stay at the 95% confidence level, so I would have 1.96 times p hat q hat over n. So with this, I can solve for a suitable value of n, a suitable sample size, that's going to make it so that when I construct the 95% confidence level, that the errors, that the plus or minus, is only going to be 0.05. In other words, I'm choosing n to rig the calculations so that when I go through this whole procedure, the plus or minus part is going to just be 0.05. All right, so next time we'll talk about a couple other things that we can say if we have information about a sample. And we'll also do a lot of these things for quantitative variables as opposed to just with these categorical variables.